When we were little anyway, black holes were just kind of a figment of Einstein's imagination. They're a consequence of his general theory of relativity, but it wasn't until we had observations that people realized these things actually happen.
When you draw a black hole, what you're basically drawing is not the black hole itself, but the boundary of the black hole, called the event horizon. And inside this boundary is basically not a part of our universe. As we discovered, there are two kinds of black holes. There are black holes that have masses a few times the mass of the sun.
And the other kind that we know that exists are called supermassive black holes. These are 1 million or more times the mass of the sun. The ways you observe these two different kinds of black holes are slightly different.
We use ground-based telescopes that to watch the star orbiting around the black hole, and we've set up a telescope system in Chile using some of Yale's telescopes. We call this the SMARTS telescopes for this purpose, to watch the companion stars and the material begin its journey down to the black hole. As the stuff falls onto the black hole, it heats up and emits much more energetic radiation, and that we observe with NASA's orbiting observatories.
For the supermassive black holes, we use the Yale Keck telescope to study the galaxies surrounding the black hole so that we can try to discern whether there are visible effects on the stars and the material in the galaxy from this active black hole that's accreting at the center of the galaxy. Material falling onto the black hole forms a disk. So it's orbiting the black hole in a disk. And it needs to slowly lose energy. Physics students will know it needs to lose angular momentum before it can fall in. And what happens in the supermassive black hole case, which is really important for Fermi, is that matter flowing in, some of it goes into the black hole, but some of it shoots out in sort of energetic jets of particles that are flowing out in both directions. Very narrow, very highly collimated jets that flow out in both directions, and they're moving at nearly the speed of light. So it's a tremendous amount of energy, and we don't actually understand the accretion process well enough to know how the material going in is collimated and formed into these energetic jets. And that's one of the mysteries that Fermi is going to help us with.
And one of the things that we're observing most intensely here at Yale is a category of these black holes called blazars. Blazars happen when this jet of material comes straight at you. So we're down here, here's our eyeball or our observatory, and the jet moving at a large fraction of the speed of light is coming straight at us. And so that provides some of the most energetic radiation you can observe.
Over the whole universe, there are lots of these things, and they're pointing different ways. You know, there's a jet pointing that way, there's one pointing this way, there's a bunch that are not pointing at us. So we're not special. But the one that is pointing at us, there's an effect of special relativity, another of Einstein's theories, that makes it 1,000 times brighter than it would otherwise be. So the ones where you want to study the jet and the accretion process, those are the blazars, and those are what Fermi detects.
And so shortly after the launch of Fermi, when the Fermi team released its first picture of the whole sky, what we discovered was that a particular one of these things, which was not well studied before or particularly thought to be special, happened to be very, very energetic. It was the brightest object in the gamma ray sky, this hitherto relatively anonymous object. And so we turned all of our telescopes to watch this exciting object as this black hole presumably accreted a big lump of matter and shot it back out at us. And
made a bright light bulb.
Yeah.
For the specialists, they go by funny names. I think it's interesting to just say 3C, we don't call them, you know, Charles or Meg. We call them some strange number from a catalog, 3C 454.3. But every astronomer knows what that means, and they know what this object is. And we want to understand how accreting matter gets energized by the black hole. and how it gets ejected at these speeds. And so by studying these blazars, we hope to answer those questions. There are two things that matter, okay? We get light, okay? All of it is light. What matters is the wavelength of the light and how bright it is as a function of time. We refer to the light often as photons, which are packets of light. So we might ask, how many photons do we get as a function of time? I mean, astronomers
photons per second.
Photons per second. So we might draw a plot that looks at the intensity of an object, a black hole, let's say a blazar, as a function of time. And we quite frequently see variations where it gets bright and then it gets dim and all manners in between. And the beauty of the research we're doing here at Yale, using the SMARTS telescopes and the Fermi Space Telescope, Gamma Ray Space Telescope, is that we can look at this light curve in the optical wavelengths. These are wavelengths, this is the light your eye sees. And then we can plot the gamma ray light curve at the same time, and we'll see that it more or less follows the same trajectory.
And the new stuff over the past couple of years is that for the first time, we're able to get a light curve like this of intensity versus time in the optical and in the gamma rays at the same time for the same objects. That's what the combination of the Fermi satellite and our telescopes in Chile can do. And so for the first time, we've been able to confirm that they do go up and down together. And that, it turns out, rules out a whole bunch of different theories about what might be going on and confirms some other ones. And the exact details of how these wiggles line up is what we're working on now, and that's going to give us a whole bunch of details about exactly what's going on in this jet as stuff is shot out of a black hole at close to the speed of light.
These blazars are billions of light years away.
They're half a universe away.
Half a universe away, and they're emitting, billions of photons in all directions, and we get a few hundred or a few thousand, a piddling amount. We can figure out what the physics is in this object. That's just amazing to me.